You have been coding for a while now. You can build things, you can follow tutorials, you can add a feature when someone tells you exactly where to put it. But then you open a real code base, one you didn't write, and something happens. You feel lost. Not because you don't know the language, you know the language. Not because you don't understand the syntax, you understand the syntax. You feel lost because you don't know what you are looking at. There are folders with names that almost make sense. There are files that seem to do the same thing but live in different places. There is code calling other code, and you can't figure out where anything actually starts. That feeling has a name. It's not imposter syndrome. It's not a skill gap you can close by learning another framework. It's simpler than that. Rails, Django, Spring, Next, these are different dialects. The language underneath them is the same. Nobody ever showed you the skeleton. Every serious software system, every production codebase you will ever work in is built on the same underlying structure. The same forces, the same decisions made over and over again across every language, every framework, every decade of software development. This video teaches you that language. By the end of it, you won't just understand the concepts, you will be able to walk into a code base you have never seen and immediately read it, the way you would read a building by looking at its frame before its walls. This course has 3 episodes, and all of them will be released here completely free. In this series, we are not learning a programming language. We are learning how software systems are structured, the architecture that makes them work. If that sounds useful, subscribe so you don't miss the next episodes. Let's start with one sentence that explains almost everything. Every layer in a system exists because the layer above it cannot be trusted. I'll read that again for you. Every layer in a system exists because the layer above it cannot be trusted. This single sentence explains why validation exists. It explains why service layer exists. It explains why tests exist, why CI/CD pipeline exists, why error handling exists, why monitoring exists. Every architectural decision in software is a response to a failure mode. A place where something could go wrong, did go wrong, or will inevitably go wrong. Elite programmers see the failure modes first. They design for what breaks, not just what works. Beginners see syntax. Senior engineers see surfaces. Architects see the cracks. What you are learning in this video is how to see the cracks. We are going to do that by understanding 5 forces. These aren't design patterns. They are not framework concepts. They are the fundamental pressures that every software system is always under. The forces that shape every architectural decision that has ever been made. Once you understand these 5 forces, architectural decisions stop seeming arbitrary. They start seeming inevitable. The first force is trust. Here is the situation. Your system is running somewhere. A server, a cloud instance, it doesn't matter. And the outside world wants to talk to it. Users sending requests, other services sending data, APIs calling your endpoints. And here is the fundamental, uncomfortable truth about all of that. You cannot trust any of it. You cannot trust any of it. Not because people are malicious, though some are, but because even well-intentioned data is unpredictable. A user submits a form and leaves a required field empty. Another user pastes text with characters your system doesn't expect. A third-party API sends you a number where you expected a string because they updated their schema and didn't tell you. None of these people are trying to break your system. They are just doing things, and your system breaks anyway. Now think about what happens if untrusted data gets in. If a string arrives where a number was expected and your code just passes it along, it travels deeper and deeper into the system. Each layer assumes the data is clean because some previous layer was supposed to handle it. And eventually something breaks, not at the boundary where it should have failed, deep inside, in a function that was never designed to deal with a bad input, producing an error that has no clear cause. That's the trust failure mode, not a security breach, just corruption, spreading silently inward. This is why validation exists. This is why schema exists. This is why typed systems exist. Every check at a boundary, every is this the right shape, the right type, the right range, is a response to this force. You are drawing a line and saying data can only cross this line if it meets these conditions. Everything else gets rejected here at the surface before it can do damage. Think of it like a hospital. You don't let someone walk directly into an operating system. There are checkpoints, triage, verification. The operating room trusts the data it receives because something before it did the work of making it trustworthy. Every validation layer in a software is that checkpoint. The further inward data travels without being checked, the more dangerous it becomes. The trust force never goes away. It exists at every boundary where your system meets something it didn't create. Your job is to take it seriously at the right place, not pretend it doesn't exist, and not check the same thing 15 times in different layers. The second force is separation. Here is a thing that happens constantly in software, especially when systems are young and moving fast. Two concerns end up in the same place. Your root handler fetches from the database. Your component makes the API call. Your service function formats the response for the UI. Each of these feels like a small convenience in the moment. You are already in that file. You already have the data. It's just two more lines. And then you try to change something. You want to change how the database query works. But the query is tangled up with the HTTP response formatting. You want to unit test your business logic. But the business logic is inside a React component tied to rendering. You want to reuse a function, but the function has a direct dependency on 3 other things it shouldn't even know about. This is the failure mode of ignoring separation. Things that were supposed to be independent become coupled. Coupled things cannot change independently, and systems must change. They always change. The rule is straightforward. Each piece of system should know exactly about one concern, not because it's elegant, because it's practical. A route handler that only knows about routing can be changed without touching business logic. A service that doesn't know anything about HTTP can be tested without spinning up a server. A component that only renders state can be tested without mocking an API. Here is the test. Look at any function or module and ask, how many different reasons could this change? If the answer is more than one, something is wrong. It knows too much. It's doing too many jobs. Two different futures are competing inside a same piece of code. Every layer in a well-designed system exists as a response to this pressure. A root layer exists so that HTTP-specific concerns don't bleed into business logic. A service layer exists so business logic doesn't bleed into database queries. The component layer exists so UI rendering doesn't bleed into data fetching. Each layer is a clean surface. What happens on one side doesn't leak to the other. Separation isn't about following rules for their own sake. It's about keeping the future costs of change low. The third force is state. State is any value that can change over time. The user's name, the contents of a cart, whether a model is open, whether a request is loading, these are all state. And state has a nature, a kind of gravity. It wants to multiply, it wants to live in more than one place. Here is what this looks like in practice. You fetch a list of users from the server. You store it in a component's local state. Then you fetch it again somewhere else and store it there too. Now you have two copies of the same data. They start out identical. They will not stay that way. The user updates their profile. One copy updates, the other doesn't. Your system now has two different answers to the question, what is this user's name? And no clear way to know which is right. This is the failure mode. Not that the state is bad, the state is necessary. A failure is a state living in too many places, with no single source of truth. The state force is the constant pressure of the state wanting to spread. And your architecture's job is to contain it. Every cache, every state store, every synchronization mechanism exists as a response to this force. The fundamental principle is simple. A given piece of state should live in exactly one place. Everything else that needs it reads from that place. Nothing else has its own copy. On the front end, this is why we separate server state from UI state. The user's data comes from the server. That's the server state. Whether drop-down is open is UI state. These are fundamentally different things. Server state has a source of truth outside your application. UI state doesn't. Treating them the same way creates the wrong architecture for both. On the back end, this is why databases are the source of truth and cache are not. A cache is a performance optimization. It is not the truth. The database is the truth. The moment you treat a cache as the source of truth, you have lost the track of where a state actually lives. The rule: know where every piece of a state lives. Know who is allowed to change it. Know how everything else gets notified when it does. If you can't answer those three questions for a piece of state in your system, you will eventually have a bug you cannot explain. The fourth force is change. Systems always change. This isn't a possibility, it's a certainty. Requirements change because the business learns something new. A data model changes because the original assumptions were wrong. The API changes because a third-party service changes. The framework changes because a better one exists. Code written today will be modified by someone for some reason at some point, always. The question isn't whether your system will change. The question is what it costs when it does. In a poorly designed system, a single change touches many things. You change a database schema and you have to update SQL in 12 different places. You rename a field and something breaks 3 layers away that you didn't even know existed. You add a parameter to a function and now 15 callers need to be updated. This is the failure mode. Change that should be local becoming a change that is global. Every abstraction in software exists to fight this force. An interface is a promise about what something can do. So you can swap the implementation without changing the things that use it. A schema is a contract about what data looks like, so the layers that consume it don't need to know how it was produced. A service layer is a boundary, so changing the database doesn't require changing the HTTP layer. Good architecture means changing one thing without breaking 10. When you look at a system and wonder, why is this wrapped in an abstraction? Why not just call it directly? The answer is almost always the change force. Someone at some point knew that this thing was likely to change, and they built a layer so that when it did, the blast radius would be small. This is 12 files, 12 places to find, 12 places to update, 12 places to get wrong. One abstraction, one single boundary would have contained all of this. The change would have happened in one place and nowhere else. Abstractions are not complexity, they are control surfaces. They are the decision to pay a small cost now so you don't pay a catastrophic cost later. The fifth force is failure. Every component in your system will fail, not might, will. The network will drop, the database will time out, a third-party API will return a 500, memory will run out, a deploy will introduce a bug, a dependency will change without warning. These are not edge cases. These are the normal operating conditions of production systems. Any system that treats failure as an expectation rather than a design constraint is not a system. It is a gamble. The failure force is this. Every component has a failure mode, and those failure modes compose. A database timeout causes a service to hang. A hanging service causes requests to queue. Queued requests consume memory. Memory exhaustion crashes the process. One small failure becomes a cascade. This is why every layer in a well-designed system has a failure strategy. Not just happy path, a failure path. What happens when the database doesn't respond? Does the request hang forever, or does it time out gracefully? What happens when an external API returns an error? Does the system crash or does it degrade? What happens when a function throws an unexpected expectation? Is it caught at the boundary and reported, or does it propagate silently upward until it crashes something that had no reason to fail? The questions, what does this do when it works and what does this do when it breaks, are equally important. The second question is the one that separates systems designed by engineers who have been in production from systems designed by engineers who haven't. Every error boundary, every retry mechanism, every circuit breaker, every fallback, every health check, these exist because someone took the failure force seriously. You don't build for failure because you expect everything to break. You build for failure because you know some things will, and you want the system to survive them anyway. This is what it looks like when the failure force has been taken seriously. Not a system that never breaks, a system that was built knowing things would break and designed to survive them anyway. That is the difference. Five forces. Let's name them one more time. Trust. Data from outside cannot be trusted. Every validation layer exists here. Separation. When two concerns mix, neither can change independently. Every service layer, every repository, every clean interface exists here. State. The state wants to multiply. Every store, every cache, every source of truth exists here. Change. Systems must change. Every abstraction, every interface, every contract exists here. Failure. Every component will fail. Every error handler, retry, and fallback exists here. These five forces are always present. They don't disappear because you use a framework. They don't disappear because you follow a tutorial. They are underlying physics of software systems, the forces that architectural decisions are responses to. When you see a layer in a system and you don't understand why it exists, ask, which force is it resisting? The question almost always has an answer. When you are designing something new and you are not sure how to structure it, ask, which of these forces are relevant here? That question will point you toward the right architecture more reliably than copying a pattern from somewhere else. These five forces were present in the first software ever written. They are present in every system being built right now. They will be present in every system built after this. They don't care what language you use. They don't care what framework you pick. They are just there, always. Now here is how you use what you have just learned. Look at any piece of code, any function, any layer, any module, and ask three questions. First, what does this know about? A route handler that knows about SQL, something is wrong. A component that knows about network requests, something wrong. A piece of code should know exactly as much as it needs, no more. The moment something knows too much, you have found a separation violation. Two concerns have merged where they shouldn't have. Second, what does this trust? Where did this data come from? Was it violated? At what point in the flow did it become trusted? Trust is not a setting. It's a decision made consciously at every boundary. If you can answer where data was validated, it may not have been. And untrusted data moving inward is the trust force being ignored. Third, what happens when this fails? Not if, when. Is the failure caught? Is it logged? Is it graceful? Or does it propagate silently, compounding into something much harder to diagnose? If you don't have an answer, the failure force is being ignored. These three questions are your diagnostic tools. You can walk into any code base, pick any file, and ask them. The answers will tell you whether the system is well designed or whether it has accumulated technical debt you will eventually be asked to fix. There is a progression in how engineers understand software. At the beginning, you copy code without knowing why it works. Then you learn the syntax. You know what the code says, but not what the system does. Then you learn features you can add to an existing system, but you don't understand why it's shaped the way it is. Then something shifts. You start to understand the layers. You understand what each layer is responsible for. You can reason about where new code belongs, and eventually you understand forces. You understand why each layer exists. You can look at a code base you have never seen and read it, because you know what pressures shaped it. That's what we are building toward. In the next video, we walk the full system layer by layer, from the moment request enters your backend to the moment component renders it on screen. Every layer, its purpose, its failure mode, and the forces it was built to resist. You have just learned how to see the forces. Next, you see the layers. See you there.